So as I said, I'm Mark Shapiro. I work in Paris at INRIA and at the university, the Science University, Pierre and Marie Curie over there. So today we will, with Nuno, we'll tell you a little bit more about CRDTs. I assume that most of you have read the papers, so we will not go too much into the detail of what a CRDT is, but more about the design philosophy and what we've learned in the past few years. So we all know about cloud computing and the problems we have with cloud computing. We have replicas, we have databases that are replicated in different data centers, latency, failures, etc. So for all these reasons, you're going to replicate the data in different places, move the data as close as possible to the users, have your application logic running next to the database, and in order to have availability, you want to be able to accept reads and updates at all the different replicas without synchronizing, because synchronizing is costly and is not available if there's a problem. So this is where our starting point, and what we've been trying to do is make this a lot easier for programmers. Of course you all know about key value stores and NoSQL databases, but we're trying to move one level up to higher level abstractions that are more useful to the user, to the developer. And another thing we want to do is look to the future. So today there might be a few tens of data centers around in the world, but this is changing very quickly, and there's more and more and more locations for your data that are possible. The 5G revolution is coming very soon, where the phone operators are going to put a data center in every base station. So there'll be thousands and tens of thousands of data centers around the world, and you're going to have to put your replicas in there and manage that. And you will want to be able to move your application logic really, really close to the user, so he's only a few microseconds away from keystroke or mouse movement to response. And what we want to do is we want to move the guarantees that we might give today in the data centers to those replicas very close. So, we're not there yet, obviously, but sometime in the future we'll have to be able to manage, tens of thousands of replicas, and of course do that in a fault-tolerant way. So, the approach we have proposed is called conflict-free replicated data types, CRDTs, and the insights here are, first of all, it's a data type, so it's well encapsulated, and you sort of hiding the ugly aspects behind a nice, interface which is familiar to users. Of course, it's replicated at multiple nodes, but the way it's replicated is that in order to ensure availability, first of all, we are always ready to accept updates, so therefore updates can be concurrent and non-synchronized. But we still guarantee that your data will eventually converge. And it's not just registers that do reads and writes, it's higher level data types such as sets or graphs or sequences or complex things that are much more useful for application programmers. And I will not go into the details of how we prove this, but it's in the papers. If you just follow it says mathematical properties, but it's just really some very simple design rules, you will ensure that these things will converge. And thanks to this design, everything is decentralized and everything happens in a very peer-to-peer manner. So why would anybody use these data types? Well, first of all, because they ensure availability. If availability is not your prime motive in life, forget CRDTs and forget parallelism. Might as well do things sequentially. It's a lot easier, a lot simpler, and much more familiar. So if availability is your thing, then maybe CRDTs is something you want to look at. CRDTs are, as I said, higher level data types. So if you don't need higher level data types, right? If just read-write registers, key value stores are okay for your application, by all means stick with that. But if you have like I don't know, some distributed game with game state that is highly mutable and highly distributed, over these 10,000 replicas. Again, maybe this is something you should be looking at. Mobile computing is another example because your mobile computers might be completely disconnected from the network, and you want to be able to do your reads and updates even though you're disconnected, and be sure that you're going to reconverge when you reconnect. It's also useful within the data center to have more parallelism inside the data center. Avoid synchronization. So some of the concepts, some of the design ideas. So first of all, these are data types that are supposed to be familiar. So a CRDT set should look as closely as possible to your sequential set, right? And it has the same operations to add and remove elements in a set, and a graph should look like a graph, etc. But of course, if you want concurrency, then you have to accept some, you need to lower your expectations somewhat, okay? But anyway, you need to be, the sort of top level bit is you need to be backward compatible with sequential data types. So this is not written in the papers. It's so obvious that we never state it, but it's actually a very important property. And the second principle is you want your operations to commute, okay? Because if you have operations that updates that commute, right, then it doesn't matter which order they're received. So if I do, some operation up here, U, and some other operation down here, V, somebody might receive U followed by V, somebody else might receive V followed by U, but it shouldn't matter, right? So if your operations already commute in the sequential data type, you're home free, right? So you have things like, if I'm talking about a set, I have operations like adding an element E and removing a different element F. Okay, that commutes because add E followed by remove F, E is in the set, F is not in the set, and that's true even if you swap the two. So naturally, concurrent add E and remove F should have exactly the same semantics, okay? But if your operations do not commute, okay, then you have a design choice. And what you need to do is ensure that these two concurrent operations that do not commute in the sequential sense still come up with it doesn't matter whether I receive. So for instance, removing and adding the same element, right, sequentially does not commute, right? If I do remove E followed by add E, I expect E to be in the set. But if I do add E followed by remove E, I expect E not to be in the set. So I have to make some choice, some design decision. So it has to be deterministic so that all the replicas come to the same conclusion no matter what order they received these operations in. So it has to be deterministic. That's really the sort of the essence of CRDTs. But it also should be explainable to users and developers. So you want it to be as close as possible to one of the sequential execute. It cannot be exactly the same, okay? And sometimes the anomalies will show through, but it should be close enough, let's say. There's no good measure, but close enough. So basically you will say, well, if I have concurrent remove E and add E, I will choose one of these two solutions maybe. I will decide that, well, in that case, add should win, or maybe I'll decide that remove should win, but it doesn't matter, it has to be deterministic. Okay, and of course you don't want to lose updates, right? So last writer wins approaches, for instance, that are widely used in key value stores, they work, they commute in this sense, but they're ugly because you lose updates. And the stable preconditions I will talk about in a minute. So CRDTs are an academic concept that were published in 2009, and the main paper is 2011. But they've been picked up by industry, and these are some of the companies, well, these are the companies that we know about that have announced in some way or another that they're actually using CRDTs internally. So we must be doing something right here. And I will talk about one of these guys, and there's probably some people from Bet365 in the room, so they will correct me if I say anything stupid. This is knowledge I know from their website and videos that they posted. I don't have any particular inside knowledge. okay? But, okay, so these are, apparently, they say, the largest European online betting operator, and they have a very bursty load. They have up to 2.5 million users at any point in time, simultaneous users banging on their data. 1 terabyte working set. I'm not sure what's in that working set, but I know that a substantial fraction of that working set is actually stored in CRDTs. And sort of the top level requirements is, for them, is that it has to be available. So users have to be able to place their bets at any point in time in whatever their soccer game, and you know, even if one of their server fails, and they also want the results to be understandable. So just eventual consistency is not good enough. You have to have some kind of monotonicity. That is, if I made a bet and I look at the database, I should be able to see my bet, right? Or if I read somebody's, you know, some result, somebody made the bet, a minute later I should look at the database and still find it there, right? You don't get those guarantees if you just ask for eventual consistency. And they want transparency. That is, they want the results to be explainable to users. So again, this is why I think probably the reasons why they chose to look at CRDTs. And in the old days, a few years ago, they used SQL Server and found that didn't scale at all, and that when they had a failure, it took hours for the system to reconverge. And mid-2013, they decided to look at REAC, which is a NoSQL database, which was fine in terms of availability, but when a failure would occur, they would have siblings, and this was really so multiple values to the same data item, which was very hard for them to deal with manually. So at some point they decided to look at CRDTs, and they're actually using CRDTs in production since almost a year now. And what they're using is the observe remove set that has been implemented by Russell in REAC. Again, I don't know the details of how they use it, but basically they just put those bets in a set, and at some point they look at the set and see which bets match. And what they say is that this was really transformational for them, that their developers from this point on could concentrate on developing interesting applications and not concentrate on debugging anomalies in distributed systems. And whenever there was a failure, it would reconverge very quickly and correctly. And I asked them, what would they like for the future? What's their wish list? And so the wish list is more of the same, right? So they would like, the same, availability and all that, but, a little bit more guarantees about, maybe I want to update 2 things at once and not just a single set. So I already talked a little bit about this. I can skip this slide. So sets is sort of the poster child of CRDTs, and this is the thing that everybody's been looking at. But I didn't want to make it too boring, so let's invent a new data type, okay? A new CRDT, right? So you're starting you have this idea for a new startup. You're going to manage wedding lists for people who get married, and everybody will have a copy of their wedding list on their iPhone. And okay, so here's my wedding list. It has, I want a TV, and I want my honeymoon in Venice. And it's an ordered list. As TV, buying the TV is more important to me than going to Venice. And then, of course, I might, add things. So I will point at one of the items in my list, and I will say, well, I want to add something right after this one. Okay, so I want books. Less important than going to Venice. And after all, no, maybe I don't want to go to Venice, so I will delete, point at Venice and say delete, right? And then, my spouse, to be, on her replica will also point at Venice. She doesn't know that I deleted Venice, right? Because we're working independently on different replicas. So she points at Venice and says, well, I would also like to go on a ski trip, but Venice is still more important to me. And then at some point, the data will be exchanged and we will reconverge, and now you see that Venice is gone, right? And that all the things that I have added are in there, and they're in the right order. Okay, so yeah. So here's the specification. I want to be able to look up the contents of my wish list. I want to be able to add a wish to my list, and I want to remove something from my list. Easy enough. So how can I implement that? Well, basically, it's a linked list, right? I'm adding and removing elements to a sequential linked list. Has a beginning marker and an end marker, and every time I want to add something, I will just say add after this position, right? So let's start with, the list that contains TV in Venice, and then I will add laptop by, just doing the usual linked list thing. I replace the, next pointer that is in the Venice node with the pointer to laptop rather than the pointer to the end, and laptop points to the end. You all know how to do linked lists, right? And then I can do the same thing. I'll insert books, and then maybe concurrently, oh no, and then I'm deleting Venice. Okay, so deleting, I'm not allowed to remove Venice from the list immediately because my spouse might be adding things after Venice, right? Which is exactly what happened in the example I showed you. So I can still insert the ski trip at the right position, okay? So what happens if on two replicas we insert two things at the same position, right? So I want to buy this new drone that Apple just came out with, and my spouse is less materialistic than me, and she wants world peace, okay? So we have to resolve this. Just any old way of resolving it is okay, as long as it's deterministic, right? So let's just resolve it by alphabetical order, and we're done, okay? And there you have the data type that you needed for linked list. So I cheated. I didn't really invent this. This is called RGA, and it is in one of the CRDT publications, but it's a little bit obscure. Okay, so maybe we can improve this, right? No, this looks wrong, right? I mean, world peace definitely cannot be less important than buying a drone, right? I want to move world peace up to the top, right? But simultaneously, my spouse says, oh, world peace, this is, doesn't make any sense. World peace is not achievable, so it doesn't belong at the top of the list. I'll move it to the bottom, right? And, well, we end up now with world peace in duplicate, of course, okay? So something went wrong here, right? This is something that, I asked for move, right? I asked, which implicitly means this thing cannot be in two places at the same time. If it is in two places at the same time, by the way, I've messed up my linked list, but that's just a technical question. So in effect, I've just added two copies of world peace and removed the single one. So I didn't get what I wanted. And the other thing, of course, I would like to do is, now that I have my wedding lists, people are going to buy me my presents, right? So my father is going to say, okay, I mark the iDrone as being, I'm going to buy you the iDrone. And then Russell, who really likes my spouse, also says, oh, I'm going to buy you the iDrone. And we end up with two copies of the iDrone, right? Which, again, is not what we wanted. So what happened here? So what's the difference between remove, which just marked something as being removed, and offer, which also just marks something as being offered, okay? Well, there's a big difference. So here I'm writing a specification in sort of the Hoare triple style. So here I have an operation, remove, and then to the left is the precondition, the things that have to be true before I apply this operation, and to the right, the postcondition, the things that should be true afterwards, right? So when I remove, I expect the thing that I'm removing to be marked as a tombstone, okay? But it doesn't really matter what the state is before. Even if it was a tombstone before, it's okay, right? So there is no real precondition. It's marked as true here. Whereas in the move case or in the offer case, I want to make sure that the item is unique, right? So this invariant that this item appears only once, right, comes out in this precondition, right? So in a sequential execution, if I want to offer something, I make sure that it hasn't been offered before, right? So I have this precondition. It's not offered yet, and I offer it, and therefore afterwards, it will be in the offered state. But now you see, just looking at this, you see that if I have two concurrent offers, executing one of these offers is going to violate the precondition of the other one, okay? So this is really the reason why move or offer didn't work, okay? I'm trying to maintain an invariant, and in order to maintain that invariant, I need a precondition, but the concurrent operation is violating that precondition. So I'll say the precondition is not stable. So, and the people who came to our tutorial yesterday, we explained this in a little bit more detail. Basically, there's a proof that says that if all the invariants are, if all the preconditions are stable under all concurrent updates, then the invariant is guaranteed. But if not, all bets are off. So a few lessons learned before I pass the mic to Nuno. So if you want availability, you have to accept concurrent updates. And there's undesirable effects. But you can often mask those undesirable effects. So for instance, if I add the same thing twice, okay, it's okay, right? I can accept them both and just sort of hide the second item, right? I want to be backwards compatible. So this, if someone uses my CRDT in a normal sequential program, it should have exactly the same effects as the sequential data type. If two operations commute, then I want the concurrent semantics to be the same, but otherwise I have to choose something that is deterministic and close enough. And now if I want to maintain invariance, this is something really new that is not in the papers. If you want to maintain some invariance, then the thing you need to ensure is that your preconditions are stable.
Okay. So now I will try to explain you how we can maintain some of the invariants. So if you look at many applications, so many applications need to enforce invariants of the form kind of some counter must be greater or equal to k. For example, if we are counting the number of add impressions in an application that has some amount of ads to print, so the number of impressions left must be greater or equal to 0. If we keep the money, virtual money in a game, okay, we want the virtual money to be greater or equal to 0, of course. If it's real money, we also want it the bank also wants the money that you have in the bank account to be greater or equal to 0. So it's exactly the same problem. So how can we try to address this problem? One thing that is important to understand is that if you are trying to for example, to keep the number of impressions left greater or equal to 0, most of the times we don't have problems. If the number of impressions left are 1,000 or 20,000 or something like that, so decrementing by 1, well, it will not make it under 0. Okay, so only when we are closing to 0, we get into problems. Okay, so to try to address these numeric invariants, what we do is we try to see the current value of a counter, okay, as the number of writes to execute a decrement. For example, if I have a counter x and the value of the counter, for example, is 1,000, that means that I have 1,000 writes to execute decrement. Okay, and I can pick these 1,000 writes to execute decrement and distribute these writes by multiple replicas. Okay, so every time I execute a decrement, I will consume 1 write. Every time I execute an increment, I create a new write. Okay, so and this is the key idea to enforce these numeric invariants. Okay, we'll have these rights. We'll distribute these rights among replicas. Okay, and we want to not consume more rights than it exists. Okay, so the problem now is we could do that using a central server. We would go to the central server, see if there is any right available. Okay, but we don't want to do this. Okay, what we would like to do is to distribute this among multiple replicas so that each replica can access the counter independently, just like it is a CRDT. Okay, so each replica has its copy of this object. Each replica will execute operations locally. Replicas will synchronize peer-to-peer as any other CRDT. Okay, so using the normal rules, if we have state-based CRDTs, we'll send the state, we'll do the merge as in any other CRDT. Okay, there is a slight difference. Okay, so if we don't want the counter to be negative, sometimes when we execute an operation locally, the operation will have to fail. So I will try to decrement, and my replica will tell me, okay, you cannot decrement, because if you decrement, we might break the invariant. Okay, that's the only difference when compared with a normal CRDT, in which you would be allowed to decrement, but you could go negative. Okay, so we've built a CRDT that is called the bounded counter. Okay, the bounded counter, basically, you can create a bounded counter. You have one operation to increment a value. You have an operation to decrement a given value. You can see the current value in your bounded counter. And you can transfer rights from one replica to another replica. Okay, so I can give rights to another replica. I will now show how this works. So this is a bit scary. Okay, so basically we have our CRDT. Supposing that we have three replicas. Okay, as a matrix, each line corresponds to one replica. Each column corresponds to one replica. Okay, and now I will show how we update this matrix. So we start with all zeros, meaning that the current value of the counter is 0. Okay, and now I can increment in the first replica. When I increment in the first replica, okay, I will update the matrix in the position 1, 1. Okay. If I increment in the second replica, I will use the second line, second column. Okay, saying that I'm incrementing. And the same thing for the third replica. So I'm incrementing in the third replica by 8. I will use third line, third column 8. Okay. Later on, I will explain exactly what each line and column means. Okay. So now we want to do decrements. Okay, we have done increments. We can always do increments, no problem. Okay, now I want to do a decrement. So in first replica, I want to decrement by 15. I will not explain at this moment how we check if we can decrement by 15 or not, but we know that we cannot, because in that replica, I have only incremented by 10. I have not synchronized with another replica, so this will have to fail. Okay, later on, I will explain how we understand that it needs to fail. So in the second replica, I want to decrement by 5. Okay, in this replica, I can decrement by 5, and I have to record information that I want to decrement by 5. So how do I do this? So I will use the hexa column saying that, okay, I want to decrement by 5. Okay. So how do I do a transfer? So in the third replica, I have incremented by 8. So that means that I have 8 rights to do decrements. Okay. So suppose now I want to transfer some of these rights to replica 1. Okay. That wanted to decrement more than 10. So I want to transfer 4 rights to replica 1. So what do I do is I will update that information in my matrix. Okay. Basically, I use the last line. So replica 3 will always uses this line, okay, and will record that information in the first column, saying that, okay, I've transferred 4 to replica 1. It's for 8, yes, because this is the value that I've incremented, okay, initially, and this is the value that I've transferred, okay. So this is how I update the matrix when I do increments or transfers or decrements, okay. So how do I merge? Okay, so in CRDTs, when we do a merge, we send the state of one replica to another replica, okay. And in this case, merging is pretty simple. It's pretty simple because each replica only modifies its line, okay. No other, so in the first line, only replica 1 touch. On the second line, only replica 2 touches. On third line, only replica 3 touches. So to merge is just to the max of every column. So merging the first replica with the second replica is just do the max. And I could do the same from replica 3. Okay? And I would have the values. Okay? So so now let's look again how we really handle decrements. So now we have this value, okay? This value of the bounded counter, and I want to do a decrement by f12, okay? How do I know that whether I can do a decrement of 12 or not? So I need to check if I have 12 or more writes to do decrements, okay? And to do this, basically what I do is I will add the position 1, 1 in the matrix. That those are the values that I've incremented. Okay, so those are the writes that I've created. Okay, I add the values in the column, the other values in the column. Those are the writes that some replica transferred to me. So that 4 means that replica 3 transferred 4 writes to me. So I have 14 writes. Okay, and I have to decrement the values that I've transferred to other replicas and that I've consumed. In this case, I have not consumed any value so far. So in fact, I have 14 writes available, so I can execute the operation locally and guarantee that I can decrement, and by decrementing that, the value of the counter will not go negative. Okay. So, what can we do when you use bounded counters? Basically, in summary, we execute operations locally. So if there is no enough writes, we fail locally. Of course, we can try to transfer writes from other replicas at that moment. Okay, so we can redistribute writes proactively. Okay, replicas can be transferring writes among them, or they can transfer when I do a decrement and I don't have enough writes. I can ask other replica to transfer me some writes. So synchronization is using a peer-to-peer synchronization. And we have built a prototype on top of RHEAC. We have done some micro benchmarkings. Okay, so we have deployed this in Amazon using three data centers. Okay, and we compare basically a solution that uses strong consistency. Basically, strong consistency with this approach is having a single data center, and all updates will go to that data center. Okay, so the average latency is pretty high because some of the updates have to go across to some other data center. And in this case, we are using the strong consistency approach of RHEAC. So performance, it doesn't scale to very large numbers. Well, we have not so many keys. If we add more keys, probably it will scale more, but this is so for having a apples to apples comparison, this is what we have. So if we have weak consistency, and this is RHEAC with RHEAC counters, okay, basically we have much higher throughput and much lower latency. Basically, each point of this is taken by incrementing the number of clients. So for some given number of clients, I can achieve some throughput with a given average latency. So this is what this line means. So a line more into this direction is better. A line more in upper, it's worse. Okay, worse in terms of throughput and worse in terms of latency. So what we can do is something in the middle. We are not as good as React React counters, native weekly consistency. Okay, one of the reasons for this is that our objects are larger, so we have to store more information. Okay, but we are much better than having typical strong consistency. Okay, and what we also have when compared with weak consistency is that we guarantee that that invariants will not be broken. While when we use only weak consistency, when we are closing to the limits, even if we check if the value of the counter is greater or equal to 0, if you have lots of decrements being executed concurrently as they are being executed in different data centers, we can execute more decrements than we can. Okay, so this is the bounded counter. So we had a couple more slides about some system that we have done that is Swift Cloud. I will pass over these slides, but just in 1 minute, what is Swift Cloud? We have built a database. There is a paper online that you can read. The idea is that in Swift Cloud, we have, instead of having just the full database, we've cached part of the database in the client machines, okay, and allow applications to execute in those client machines, okay. I will pass all these slides, and I will just give you some numbers that I think are interesting. So we have done this. So basically the idea is we move part of the data to the client, okay? And as we move part of the data to client and allow applications to access the data that is cached in the client, okay? In these two lines, the pink and the blue, you can see that we have very good latency. Our latency is almost 0 because most of the operations go execute locally, okay? Because data will be on cache, okay? If you use a typical approach that is going to a data center, the latency will be worse because we have the time to send our request to the data center and to get the reply back from the client, okay? So there is, however, one area there that is important, and if you are thinking about moving your data to the client side, this is an important message that I want to leave here today. That is, after you have a first cache miss, so you are in the client, you are executing operations, and you have a cache miss. If you have a cache miss, you have to go to the server. Or if you are doing a complex query where you don't have all the data, you have to go to the server to fetch more data. As soon as you go to the server, you are into problems, okay? Your idea of getting your data into the client is not so great anymore because you may end up having to go to the server. Instead of going just once, you might end up going more than once to fetch all the data you need, okay? So one thing that you might do if you are trying to do something like this is, on the first cache miss, try to move your computation to the server, the rest of your computation to the server, and execute them in the server. So just to conclude, let me conclude fast. So things that we have learned from our experience and from experience of others that are using CRDTs is that applications require multiple types of CRDTs. So set CRDT will not solve all your problems, okay? So one important part is when you build applications, you want to do composition of multiple CRDTs. So the work that Russell and the bunch of people is doing, it's not Rick map, it's React map. Okay, on the React map is great. So as Mark has shown, so when you see CRDTs, you have to lower your expectation. So the system will not behave like having a single server, okay? But you can still enforce some invariants, and you can still do some interesting things. So you can do multiple key updates with high-level transactions, something that we have in Swift Cloud. I invite you to read the paper. So you might enforce causality, okay? That also helps with some invariants. You might enforce numeric invariants, as I shown with the bounded counter. And you can address general invariants using just right consistency. So that is the work that Mark mentioned it before. So with this, I finished my talk, and I can take questions. So those are co-workers. So part of the work has been due to those persons. And that's it.
Thank you very much. So, questions? Okay.
When Mark was talking about waiting lists, I couldn't help but think operational transformation. Is there some connection to this?
There's a connection. The connection is that operational transformation tries to take something that is non-commutative and flip it on its head and make it commutative after the fact, which I think is the wrong way to do it. Might as well make it commutative from the design point.
Thanks.
Any more? Questions? I had a question about the bounded counters. Write it down. Give me a second, sorry. Yeah, I wondered if you had some interesting metrics. I wonder if you had metrics on cases where a bounded counter request failed when they should have passed because the writes were in the system but not in the right location.
We might have some numbers on that, but that depends hugely on the number on whether you are doing proactive distribution of rights or not. So in our prototype, basically what we do is when the system is running, the replicas try to exchange rights between them so that they are more or less even among them. So in that case, when they are really, really close to the limit, you might end up into those situations. I don't have those numbers. In fact, in our prototype, we have kind of flagged that the client could ask to get an on-demand transfer if he really wants to do that. So
a bit like paying the cost of a cash mix or something.
Yeah,
right.
Something like that.
Thank you.
Also with the bounded counter, do you have a heuristic to determine when one replica should transfer some of its rights to another replica, or how is that decided when that transfer happens?
We don't have anything fancy. We are doing it periodically. After some time, we just transfer. When we synchronize replicas, we use that to level up the levels of rights that each replica has.
Okay, another one.
So you had this graph of strong and weak consistency. If you could go back to that one.
No.
Or not.
This one?
Yes, the one with all the data. There you go. So I gather from the names that weak provides less strong guarantees than strong.
Yes. Basically, weak is is plain React with
So with
multiple...
weak, I might overspend. I might go below 0.
Sorry?
With weak, I might overspend.
Yes, you might overspend.
Right. Does BC give you the same guarantees as strong?
BC guarantees you that you will not overspend.
And strong guarantees you will not overspend.
And strong will guarantee that you will not overspend. The difference is what was implied in the question by Russell. That is, if you have a strong, when you want to do a decrement and you have only one write available, so imagine the counter is equal to 1. You go to the central server and the central server knows, oh, it's 1, you can decrement and everything is fine. So when you have the bounded counters and, for example, if you have just one write and that write can be in any replica. So if you are doing decrement in a replica that don't have that write, your operation may fail. Okay?
So with
Well,
BC, you need to balance things across the different replicas, and with strong, you do not.
right, because you only have one replica with strong, and with BC you have multiple replicas.
So instead of using squares and these dots, you should have used apples and oranges.
Okay. So I should use apple and orange?
Yes.
He's saying they're not comparable.
What?
He's saying they're not comparable. They're comparable. They give you the same service.
They're
It's
comparable in some ways, but it would have helped to clarify what the differences are as well.
It's part of lowering your expectations, right? We're giving you something that's very close to strong consistency, but we're also giving you a lot more parallelism.
Okay.
Thank you. More questions? We tend to use the term trade-off, by the way, not lowering your expectations.
Hello. So probably a silly question, but most of these CRDTs are fine-grained data types, right? So small things. Have you done any research, or you're thinking about doing any research in which you're talking about coarse-grained CRDTs? So, for example, a graph database that is itself a CRDT.
What database?
A graph database. Do you have the graph data types, right?
We have graph data
So
type, yeah.
CSAT and...
We haven't done it. We haven't done it, but React...
Is there any value in that? Or?
React supports very large sets, so the BED365 people have several hundreds of gigabytes in CRDT. So, I mean, it's fine-grained in the sense that the individual elements are fine-grained, but the data itself is very large. And I think you would have the same, you could argue that the graph database will be very similar because the individual element is just, a vertex or an arc.
Yeah. Cool.
But yeah. The goal here is to be able to, especially the Swift Cloud, is to be able to handle very large databases, but only replicate the small part that you're really interested in, so partial replication, which is a very hard problem, actually.
So, any more questions? Oh, yeah.
So back in your wedding list example, perhaps I missed something. You had this operation where one of the two replicas could decide if they would place an offer for buying this element, but these are actually mutually exclusive. So if one happens, so you can't update the replica yet on the set. Otherwise, you would have to roll it back and change it after the fact. And
Right. Yeah, absolutely. That was the point I was trying to make, is that if you want to maintain invariance, okay, to maintain these invariants, you have to have the precondition. So the precondition here is that nobody has bid on this thing yet, right? And if you evaluate that locally, and you might read the wrong value for your precondition, okay? So in these cases, I mean, there's a proof here. I mean, the important thing is that so intuitively, yes, you understand that, maybe I need to do something here. But we have a proof that there is only two choices, right? It's a design choice. It's a design choice with only two alternatives. One is, okay, I need to synchronize. and it cannot be a CRDT anymore, it cannot be available anymore, or I have to live with lower expectations. So I have to live with the fact that two people could bid at the same time for the same thing. So this is something we knew intuitively, but now we have a proof.
Okay, any more questions? Okay, can please thank the speakers again?
Thank you.